So let's continue looking at exponential functions. So a very simple exponential function could be y equal to 2 to the power of x You can change that base to a 3. Notice how this is different than a quadratic function. The power in this case is not a 2, it's an x. Compare these three exponential functions. So we've got 2 to the power of x. 3 to the power of x seems to rise more quickly on this side of the y-axis, faster than 2, but 1.5 rises less quickly. So what happens when we change the base? I'm going to make that a variable, and then I can change it. I'm going to change it from 1 to 10. What's happening as I increase b? Let's go back to this relation. How are those points calculated? Y is just x, 2 to the power of x. So using our exponent laws, we know this one is 1, 2, 4, 8. Continuing the pattern, we're dividing by 2. So when x is -3, we have 1/8. When x is -2, we have 1/4. When x is -1, we have 0.5. X is 0, we have 1. And then 2, and then 4, and then 8. We could do this with a spreadsheet. recommend using a spreadsheet and when you want to make a table very quickly. So let's go back, and what if we make B less than 1? What happens when the values are between 0 and 1? The curve actually starts to go down instead of up. And the smaller we make B, the faster it goes down. We say it's decaying. And if you zoom out, you can see that it gets really close to the x-axis. In fact, it doesn't actually touch ever, but it gets really close. Okay, Ontario's population is projected to grow exponentially based on the relation P, where P is the estimated population and N is the number of years after 1996. The formula is expected to be valid until 2031. Sketch a graph of this relation. So we could use the spreadsheet to make a table of values. So we can start at 0, which is the year 1996. And we could go by 5s if we wanted to. So according to the formula, it is 11 million times to the power of n. So n in this case is going to be A3, which is 0 on this line. So because it's to the power of 0, it's like multiplying by 1. But if we change the exponent, we get these values. So using this table of values, we could plot a graph, or we could use Desmos to graph it. So we use P for population. And we'll use n for number of years. So we plot this, but we don't see anything, and that's because we haven't set our axes properly. We can tell from the table that the first y value, or the first p value, is 11 million. So we have to go at least up to 11 million to see anything. So I'm going to make it go up to 15. Now we can actually see the curve. I want the x-axis to go about 35 years into the future. So I'm going to go from 0 to 35. I think I need a little bit more room on the vertical axis, so I'm going to go maybe 20 million. Now I have a pretty good graph of this population growth. It looks like a straight line, but it's actually got a slight curve to it. What was Ontario's population in 1996? So we can use the graph. 1996 is at time 0. And Desmos is using scientific notation. Scientific notation because it's such a big number. So that's 1.1 multiplied by 10 7 times. So 1, 2, 3, 4, 5, 6, 7 loops. What is the projected population for Ontario in 2031? So 2031 is 35 years into the future, 35 years from 1996. So if we look at the 35-year mark, we have $16 So just over 16 million people. Okay, compare linear, quadratic, and exponential relations. So we're going to make a table of values, and we're going to compare these three relations. So let's take a look at the first differences of this relation. So 2 times A4 gives us our y values. If we calculate first differences here, so we want to do B3 minus b5 minus b4 do that for all of the pairs of y values. We see that the first differences are all equal. That tells us that this is linear. Here we're going to take x and we're going to square it. So h4 I'm going to square it. I'm going to do the same thing I did before, find first differences. So that went down by 7, so it's -7. First differences are not equal. So let's take a look at the second differences. So I6 minus I5 sorry, J we see that the second differences are equal and the first differences are different. Therefore, we have a quadratic relation. First difference. Okay, so this is going to be 2 to the power of O4 to get the first difference. It's going to be P5 minus P4, this number minus this number. How about the second differences? Those are all different too. So it's not linear, it's not quadratic, it could be exponential. So let's take a look at the successive factors. So this divided by this. P5 divided by this time by P4. So now we're getting equal factors, which means that we're going up by a factor of 2 each time. This tells us it's exponential. In fact, it's exponential growth because it's growing. It's a number greater than 1. So let's take a look at the graphs of these now. So I'm going to have to reset my axes here. I'm just going to use -10 to 10 so that I can see my line. So this line has a y-intercept of 0. It doesn't have a maximum, it doesn't have a minimum because it keeps on going up and it keeps on going down. So y equals x squared. This has a minimum of 0. It has a y-intercept of 0. It doesn't have a maximum because it keeps going upward. Let's compare that to 2 to the power of x. So 2 to the power of x doesn't have a minimum because it continues to go lower and lower. It never quite hits 0. It doesn't have a maximum either because it just keeps going up. It has a y-intercept of 1. A middle A on a piano is known as A4. Its sound wave has a frequency of 440 cycles per second, also written as 440 hertz. The table shows the frequencies of each of the 8 A notes on a piano. Show that the relationship between A notes on a piano and their frequencies can be modeled using exponential growth. So let's confirm that this is an exponential relationship. We can do that by checking the common factors. So all I'm doing is taking B4 and I'm dividing it by B3. So there are 8 frequencies and 7 different pairs. So this pair, 1, 2, 3, 4, 5, 6, 7. That's why there's only 7 2's here. These are my common factors. So this is exponential growth. We could plot these points and then take a look at a graph in Desmos if we wanted to.